Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we will be comprehensively covering all material delivered in section 2 in preparation for exam 2. So hold on to your seats. We got a lot to go through. We're going to here begin with kind of the physical properties, pressure, moisture, precipitation, moving more into kind of local to global scale circulation, and ultimately finishing up with discussion of climate and biomes. So what is water and the three states of water? Water exists in solid, liquid, and gaseous forms, and any time it exchanges or changes forms, there is an exchange of energy known as latent heat energy. And remember, latent heat energy cannot be measured with a thermometer. So water exists in air in the form of water, vapor, clouds, fog, and precipitation. Water on Earth, generally speaking, most of it is contained in our oceans, in fact, 97.2%. And then the next largest reservoir or source of water is stored in ice sheets and glaciers, which is largely not usable by humans. And then we're moving down here. The next largest source is actually groundwater, which later this semester we'll talk more about water resources. And then smaller than groundwater, this very small percent here, the total amount of water on Earth in surface and atmosphere is 0.02%, which is pretty darn small. We live on, or at least NMU here is on the shore of Lake Superior, being one of the largest surface water bodies on Earth. However, it's easy to forget how limited fresh water is on the surface of the Earth. But then here, kind of the focus of atmospheric water, as we're going to talk a lot about atmospheric properties, and then moving into kind of weather and ultimately climate and biomes. This incredibly small 0.001% of total water on Earth is contained in the atmosphere around us. However, it is an incredibly powerful and very influential driver of weather and climate. So some basic fundamentals, some properties of water, especially water in the air, include humidity is the amount of water vapor present in the air. And this is dependent on temperature. And as we've practiced, warm air can hold more water vapor than cold air. It's good to practice that statement and then practice it the other way around. So cold air can hold less moisture than warm air, as it allows us to better comprehend or understand more complex processes. And so we'll practice this going both directions and apply our understanding moving forward. We're just adding here the term specific. So specific humidity is measurable or quantifiable. It's the actual quantity of water contained in a parcel of air. It's often measured as the mass of liquid or mass of total water, rather, per mass of total air. And so our atmosphere weighs something, and it has lots of stuff in it, not just moisture, not just water. And so when we quantify the mass of water vapor per unit total mass, this is what's known as specific humidity. Globally, there's more water in the atmosphere as water vapor near the equator, and so low latitudes, because warm air can hold more moisture than cold air, and because there's an incredible amount of surface area of ocean exposed in that location. So it's this perfect recipe, if you will, for lots of moisture, whereas higher latitudes closer to the poles are much colder, and cold air holds less moisture than warm air, and therefore there's less humidity, literally less specific humidity. The quantity of moisture in the atmosphere in high latitude regions is substantially smaller than in equatorial regions. We can also think of humidity in terms of relative humidity, so the ratio of specific humidity to maximum humidity. And so at any given or any specific temperature, and so if it was 72 degrees in this room I'm in right now, there's this maximum amount of humidity that our air parcel can hold, and then there's an actual amount, the specific. And so now we're thinking the relative amount, which is as relative humidity increases, we're getting closer and closer to what is saturation. And so we'll explore that more here moving forward. But if it was saturated, then in our room, literally, you would see fog. There'd be dew on the ceiling or dew on the desk in front of you. There'd be condensation would be occurring. And so if that isn't occurring in front of you, then it means there is some relative amount of humidity that's less than the maximum value. A good way to understand this concept of all of the humidity terms, but here we'll practice relative humidity and this concept of warm air holding more moisture than cold air. And so on any given day in many locations around the world, we can have these fairly dramatic temperature changes. And so it's cold or cool at night, and then it gets warmer and even warmer during the day, and then it kind of like cools back down. And so the reason that we see like ground and other types of fog often is because of this temperature change. And so here we're going to track this cube of water. And so we have the same amount of water. The quantity hasn't changed, the specific humidity value. However, we're going to observe here our relative humidity value changing quite dramatically as temperature changes. And so, for example, at night when it's cold or cool outside, your maximum humidity value is lower, the ceiling is lower, and therefore your air parcel holds less moisture. And if it's at saturation, you'll see fog, you'll see clouds, it might be raining, there's dew on the grass, and that means you are at 100% relative humidity. As the sun comes up and we receive radiation and the temperature increases, warm air can hold more moisture than cold air. And at 61 degrees, that ceiling essentially here has doubled, meaning that our relative humidity is decreasing as temperature increases. That's a really good take home to practice. As temperature increases, relative humidity decreases, assuming that the quantity, the specific humidity, did not change. Flash forward even further, it gets warmer, and it's actually warm air can hold exponentially more moisture than cold air. We haven't changed. It has the exact quantity, the specific humidity. However, our air parcel can now hold several times more moisture than when it was at 40 degrees. And so now it goes down and down and down, and our relative humidity decreased until this point. So you could then work this backwards. Cold air holds less moisture. So as the day progresses and it gets colder, essentially you just draw this as a big bell curve and it would come back down off your screen to the right, where your relative humidity would start increasing as temperature decreases. Another good take home to practice. Another way to visualize this then, and a term you may have heard of, is dew point, or specifically dew point temperature. And so when our air parcel is saturated, it's at dew point, and that temperature specifically, which saturation is achieved, is called the dew point temperature. And so there's this known physiochemical relationship. And so there is literally an established, we know exactly how much the atmosphere can hold, how much moisture it can hold at any exact temperature. So like 19.942 degrees, for example, we can quantify that, and that is this curve exactly right here in the blue, which is known as our saturation specific humidity. And so this was our observed point where my cursor is. A couple things can happen. Temperature changes, which happens every single day in most places, sometimes a lot, sometimes a little, and then also seasonally. And so here, if we were sitting like 24 degrees or so, and it cooled down from 24 Celsius down to about 5 degrees Celsius, you could reach the dew point temperature at my cursor. And if you reach that blue line, that's when condensation occurs. You've reached saturation. So that's one way, and a very common way, especially on diurnal day to night cycles, that our temperatures warm up and it gets drier, and then it cools down, and cold air holds less moisture than warm air. You reach saturation, which is when you've reached this dew point temperature, and voila, clouds form and it starts raining. Another way that this occurs, so to speak, is if you like literally pump moisture into the air, which if an air parcel's sitting above a large body of water, there's lots of evaporation. You may not actually change temperature, but literally if it gets continually evaporating and you're pumping more moisture into an air mass, you could literally increase the amount of moisture until you reach that dew point saturation. And so here, that curve, anytime you reach the blue line. So temperature changes for many reasons. Part of it's the sun as it comes out. We have this radiation and the absorption of short wave and re-emission of long wave, going back to section 1. But also temperature changes over the course of a day or from one location or the next due to pressure, and then also due to changing elevation. And so this is what is adiabatic processes. It's where temperature changes resulting from the expansion as air rises or compression as air falls. And so how this works is as an air parcel rises, which it rises for multiple reasons, we'll explore that in the near future here, but an air parcel will rise. And as it's rising, there's going to be literally less and less weight weighing down on that air parcel from above. And so as that weight decreases, your air parcel expands and it keeps expanding, and then it cools as it expands. And so your pressure is decreasing as it rises, and the temperature is also decreasing. So air cools as it rises and expands, a good take home. And then the reverse is true as air parcels descend from up high and come down low near to Earth's surface. There's literally more and more atmospheric pressure weighing down on that air parcel. It's sinking, it's compressing, and it's warming up. And so here is the basic take-homes of adiabatic processes. Air is cooling as it rises and expands, and air warms as it sinks and compresses. The dry adiabatic lapse rate is faster than the wet adiabatic lapse rate, meaning as air parcels rise when conditions are not saturated, meaning you're not in a cloud and you have not yet achieved saturation or condensation has not occurred, temperature will decrease at a known rate. And so we just learned that air parcels, as they rise, they expand and temperature decreases. That then continues once saturation is reached, it cooled to the dew point temperature, your air parcel will continue to rise and it will continue to cool, but now it's going to do so at a slightly slower rate. And so the rate of temperature decrease is less from under wet adiabatic conditions versus dry adiabatic conditions. Moisture for clouds and fog. Moisture exists in many forms within our atmosphere, and so it exists as actual water droplets as well as water vapor within clouds, including ice particles or a mixture of all of these things. And then it forms precipitation that includes rain, which is unfrozen water, snow, which is ice crystals, sleet, which is rain that fell as rain and then it froze, so it kind of pelts you a little bit before it hits the ground. And then you have freezing rain, which is liquid water all the way until it hits the ground and then it freezes, which is really challenging for driving. And then hail is actually kind of cool. It has this melting and refreezing, and it's actually a droplet of water, so to speak, that's been frozen and melted and frozen, and it keeps going through. It actually keeps bigger, getting bigger every revolution or circle it makes within a cloud. But here, hail, ice crystal that melts and refreezes. As promised, there's 4 major types of lifting, meaning there's 4 ways or reasons why air parcels rise. One of them, a very common one, is known as convectional uplift, and this is due to differential heating. It warms up more in one spot and less in another. Wherever it's warming up more, hot air rises because it's less dense, and so literally as air parcels get heated up differentially, wherever it's getting more intensely or vigorously heated up, that air parcel is rising. Orographic uplift is caused by as air masses move over a continent or over a landscape. There's literally a mountain or a ridge in the way, and that air parcel has to go up because it has nowhere else to go. So it's forced upward due to topography. And then frontal uplift, as we'll learn more about here in the near future in the next few slides, we'll talk about as different air masses, a relatively warm or a relatively cool air mass, as they come together, one air mass, always the warmer one, will rise above the colder air masses. And then finally, if you had like two fairly equal air masses that are about the same temperature, about the same conditions, humidity-wise, if they literally just run right into each other, an air mass coming from up from the Gulf and another air mass coming from the Pacific, and they're going right at each other, they have to go somewhere and they're going to go up. And so just by converging winds, you can create uplift. And so some of these explained here, we'll just kind of focus on orographic for a moment, and we'll move into some of these different processes in the next handful of slides or so. But here with orographic processes, we have air masses moving, traveling across the landscape. They then reach a mountain range or a ridge, and they're forced upward. And so on the windward side, you have air cooling at that dry adiabatic lapse rate. It reaches dew point, which is when clouds form, and then precipitation starts falling. And so your windward side is much wetter or moister as a result. And so once that air parcel reaches the top of the ridge here, then the air parcel literally descends, and warm air holds more moisture than cold air. And so as that then occurs, you're going away from dew point and your relative humidity is dropping. So air temperatures are rising, relative humidity is decreasing, and you have these persistent dry conditions on the leeward rain shadow side of mountain ranges. To explore some local meteorology associated with these properties and processes we're learning, we can think about lake effect snow. And so here, just in one slide, we had a kind of whole mini lecture dedicated to this, but then to focus on it here, a big driver is the location of the polar jet stream, which needs to be to our south, which is when we have this Arctic and polar air coming down from Canada, coming across a relatively warm lake. And so you have cold air for us moving from the north to the south over Lake Superior, and that lake surface is open, and then you have lots of evaporation, and so you're pumping a bunch of moisture into the air, and it's still pretty darn cold. And so just because this air parcel is fairly cold, and now you've added moisture, you reach saturation, clouds form, snow starts falling, and then as that air mass moves up and over topography, so for us in Marquette, and then as it goes up over Ishpeming or the similar in the Keweenaws, it's near lake level and comes up to Calumet and beyond. It's often rising close to 1,000 feet, and so air parcels cool as they rise, and cold air holds less moisture than warm air, and you often experience much greater amounts of snow due to orographic processes inland and higher in elevation away from the shore of Lake Superior. All right, so now into frontal uplift, we'll compare both warm fronts and cold fronts. And so a warm front is when a warm air mass is advancing like more rapidly and it's overtaking a cold air mass out in front of it. When this happens, the warm air rises up slowly and gradually over the cold air mass, and you have slow, steady rain occurring in front of the front. And so the front here, demarked by this red with half circle line, is the warm front. And so you have this warmer air mass moving and overtaking a cooler air mass that's out front of it. And as that air parcel rises, now your air is rising above. That air is then cooling as it rises. It reaches dew point, clouds form, and it starts raining. And then in this case, you have kind of slow, steady rain occurring again in front of the advancing front. And so it's raining before the ground surface is overtaken by that warm air mass. The reverse then, with a cold air mass, warm air is always going to rise. So in this case, when a cold air mass is moving and rapidly to overtake a warm air mass, you have this rapid, intense lifting of warm air, and it's happening then. So the cold air pushes the warm air up. That air again is cooling as it rises, clouds form, precipitation starts falling, and it does, this whole sequence happens quite rapidly, which causes intense precipitation that is then falling behind the advancing cold front. And so that is a major difference then with the warm front. And so as the cold front advances, it's going to advance and overtake you on the surface, so to speak. It'll pass by you, and then it'll start raining, and you should expect likely intense precipitation and maybe even thunderstorms. A close-up of pressure here. And so as we've learned now over the course of the semester, atmosphere weighs something, and there's a bunch of atmosphere above us. And so because of that, you have the greatest pressure near sea level. And then as you go up and up and up in elevation, you have less and less mass, and there's less pressure. And so you have decreasing pressure with increasing elevation. Is warm air more or less dense than cold air? Well, going back to temperature as a measurement of kinetic energy, warm air is less dense because as air warms up, the molecules literally are moving faster, which means they're bouncing faster, and they create more space between molecules. And so you literally have less molecules per unit volume, and then it's therefore not as heavy, so it's less dense. And so cold air is more dense, and you have higher pressures, and warm air is less dense with lower pressures. To now kind of connect this to weather systems and meteorology, at the surface, we can measure pressure at Earth's surface at any place, and they form these patterns, which is what and processes, which are now kind of like moving our way into here. And so whenever you're in a low pressure system, literally that means air is at the surface, air is converging here in bold for you, and then at the low pressure, it converges and then it rises. And so any type of circulating body of air known as a low pressure system has airflow converging at the surface from all directions. And then when it meets that low pressure center, it rises and it comes up, and then it cools, and then somewhere else it's falling back down. And so wherever you measure or can observe these high pressure systems, you have air descending from up high and then diverging at the surface. So sinking or descending and diverging. So some take-homes there: low pressure converging and ascending, and high pressure descending and diverging at the surface. Those are good take-homes to practice. So now we move into these atmospheric pressure systems, including mid-latitude cyclones. And so this is a real weather map, and one in which we previously practiced, showing a low pressure center and a high pressure center, and then showing here areas where you have lots of change of pressure over a short space, or not as much change. We'll come back to that. But we can kind of look at these large scale interconnected circulatory systems, and we'll examine this in greater detail in the coming slides, meaning that each of these are cyclonic, and they're spinning, and they're then descending and diverging under a high pressure center. So here, literally, like air is coming straight down from the atmosphere toward the cursor, and then it's going to descend to the north and to the west and to the south and to the east, away from that high pressure center. Whereas a low pressure center, going back to the last slide, you have air converging at the surface. So literally, as air is coming in all directions and coming toward the low pressure center, and then directly above my cursor, above that low pressure center, you literally have air rising vertically away from the surface. So it's converging and ascending under a low pressure center. And then these are now also circulatory. And so let's explore that a little bit more. I really like this graphic, and we've had a chance to practice it a few times. And so it shows both the low pressure center, the isobar lines, our warm front, as well as our cold front. And so a mid-latitude wave cyclone is an organized circulatory system of air assembled around a low pressure center that contains a distinct warm front and a distinct cold front. And so you can go back to those warm front and cold front slides focused on what happens when air masses collide, with warm air moving into and displacing or overtaking cold air out in front of it. And so this actually also shows precipitation. So around this mid-latitude cyclone, you can expect precipitation to be occurring in front of this warm front. And so here's your wind direction moving here from the southwest to the northeast, and it's raining out front of this advancing warm front. And then here we have air mass moving from the northwest to the southeast, and your warm air is getting rapidly lifted up above that cold front, above the cold air mass, and it's raining intensely behind the cold front. Here, other kind of like foundational or very conceptual diagrams rather of isobar with high pressure and low pressure, here showing that cyclonic. And so again, you have air descending and diverging in all directions, and then under a low pressure center you have air converging and then ascending or rising above this low pressure center. With all of these arrows, you can indicate, or the arrows indicate, the direction of airflow. And within meteorology, we always describe the wind direction as wherever it is originating. And so if the wind is coming from the north, it's a northerly breeze. So moving into airflow at multiple scales here, as these next three are kind of interrelated, but we'll generally talk about airflow, and then we'll examine it at global and then also at local scales. And so another type of uplift we talked about was convective uplift, which is the uneven heating of Earth's surface. And this really is driven by radiation from the sun. And so wherever Earth's surface is heated most vigorously, it produces this localized low pressure system, and that then we have rising air. And so the air is going to cool as it rises because there's less and less pressure. So going back to adiabatic processes, air parcels cool as they rise, they reach dew point, clouds form, and it starts raining. And then eventually they cool to an equilibrium state and they'll fall back down, and it creates its own circulatory loop. Some basics of understanding like pressure maps and interpreting them. In general, high pressure systems are always trying to move toward low pressure systems. And so wind direction and wind speeds at the surface are one thing. We'll come back to wind speeds, but just appreciate, like, on a continental perspective, a high pressure system is literally always trying to like move toward the low pressure system from high to low gradients. But then interpreting the map, anywhere you see lots of isobars in a short space, so these two arrows are the same, we're now essentially going from, from one here and then to another one. So wherever there's larger gradients, meaning there's a bigger change over space, you expect higher wind speeds, where if you go over that same distance, we haven't even crossed a single isobar interval here, and so now you have bigger space between intervals, you expect lower wind speeds. So smaller pressure gradients mean low wind speed, large pressure gradients mean high or indicates high wind speeds. And so as we'll start to explore here and continue to explore, there's a lot of reasons why wind is variable, both in speed as well as their direction. And so Earth is literally rotating and we're also revolving, but with our rotation, this creates an incredible amount of frictional force, and this is known as the Coriolis effect, also known as the Coriolis force. And so as our eastward rotation of Earth, literally, if you track an air mass, there'll be this apparent deflection to the right in the northern hemisphere and an apparent deflection to the left in the southern hemisphere. And this is caused again by the rotation of Earth on its axis, and the process being known as the Coriolis effect. So now this kind of leads us right into understanding global circulation patterns. And so at small or local scales to global scales, there's unequal heating. And we've now previously in section 1 covered a lot about how there's this tremendous amount of radiation received near the equator on any given year. And so the most radiation here occurs near the equator, where the subsolar point passes twice every year. And so for that reason, you have this kind of persistent low pressure system. It's hot air wanting to rise over the equator. And then it's coldest at the poles. And so this is a really simplified version, which doesn't actually happen because there's lots that interfere. So continents interfere, the differential heating of land and water interfere. And so we'll now begin to examine these major circulatory loops at a global scale, but they're all really primarily driven by the unequal heating of the tropics compared to further north or further south. Now you add in rotational, you add in some various low and high pressure systems that develop with land and sea interactions, and other convective loops. And so it distorts it a little bit, but that's not meant to confuse it. It's just meant to say that if things were really simple, our circulatory loop would look like warm air rising near the equator, going all the way to the pole and returning. But however, really by latitude, it's divided into three major latitudinal belts near the equator, in the mid-latitudes, and near the poles, which is what we'll explore now. And so the Hadley cell, being one of the most important large global scale circulatory loops on the planet. And again, wherever that subsolar point is located, the zone of most intense heating, you have air parcels rising above the equator, and then they're drawn poleward to the north and also to the south here. And so then at some point they equilibrate and they fall back down, creating a subtropical high pressure system, which we'll talk about next. But here a Hadley cell forming because of these intense heating of the equatorial regions, causing air to rise. And so at the surface, the air is converging at the surface. And so here these arrows showing converging wind speeds from the north and from the south above this ITCZ, which is the intertropical convergence zone, which is the location of most intense heating. And really, there's a low pressure system that covers that whole latitudinal belt due to that intense heating. And so you have air rising above this red line, and then again being drawn poleward in either direction by these Hadley cells. And so right at the red line is a term known as the doldrums, because actually right there, the wind speeds are quite low, but then as you move away and there's bigger pressure gradients, there are greater wind speeds. So we just talked about this low pressure system being really produced by this intense heating of Earth's surface, by the immense amount of radiation received near the equator. Air rises, it gets drawn poleward. Eventually those air parcels equilibrate and cool down, and they start falling. And so then as the air starts falling, literally descending and diverging, a very large or very like global or sub-global scale pressure system here, you have descending air, so air going back to refresh some of the terms we learned earlier in this review. Air parcels will, as they descend, they are getting smaller, they're getting more pressurized, and they're getting warmer. And so descending air parcels warm up as atmospheric pressure increases, and warm air can hold more moisture than cold air. And therefore you have these persistently hot, sunny, dry conditions occurring at the subtropical regions, kind of north 30 and south 30, which happen to correspond with the world's largest deserts and arid climate systems, as we'll learn later. And so you have descending and diverging air under these subtropical high pressure systems. Please be aware there is a mid-latitude cell known as the Ferrel cell. And while it is interesting, I think for this course, we're going to largely skip over it conceptually, so you will not see any content about the Ferrel cell in any quizzes or exams. But I do want to focus a little bit on the polar front, as really this Hadley cell is an incredibly powerful and like really drives weather and climate across this huge scale of Earth. I mean, think about how much of Earth is encompassed between north 30 and south 30 latitude, and it's all really like incredibly governed or driven by these Hadley cells. And then here also going from north 90 to 60, these polar cells really kind of like pushing around the mid-latitudes, if you will. And so let's think about this polar front. It's this line that demarks the polar cell from the mid-latitude. And that along that polar front is what's known as the polar jet stream, which contain these really high altitude, high wind speed gradients. And so we have these intense temperature and pressure gradients on either side that set up this kind of conduit, this jet stream, literally, of highly concentrated, high speed winds. And so in some cases, when you have a really like strong pressure gradient, there's a big change from pole to mid-latitude. You can actually have this nice kind of circular pattern. But as those pressure gradients change, you have undulations, and it kind of looks like whipping a rope a little bit. And so often you'll have these big dips in the polar front or the polar jet stream going from like 40 or 50 degrees north all the way down to 30 degrees north. And these big dips right here are known as Rossby waves, which are big undulations in that polar front, which for us, often thinking about lake effect snow and winter, really cold conditions, whenever our jet stream is further south of us going through like Georgia, for example, or Florida even, we have these like cold polar and Arctic winds being drawn from the north to the south. And so here is a graphic of the Hadley cell, and here's a graphic of the Ferrel cell, and then here is a graphic of the polar cell, and they're all circulatory in this nature. So closer to 60 degrees north or south, you have air being drawn poleward and then descending and diverging near the pole and then being drawn across from poleward down south under the polar cells. Here then to kind of refocus on the ITCZ, this really the location of the intertropical convergence zone is very much just following the subsolar point. So to go back to section 1 of this course, due to our tilt and our revolution around the sun, you have that subsolar point migrating north and then south as that location of most direct intense heating. And then with it, then the ITCZ, that convergence zone, the low pressure is getting drawn north and south, and that is a pretty huge range. And so places all across the world, especially in that 20 to 30 degrees north or south range, experience what are known as monsoonal climates. And as a result, they have these like really kind of dramatic wet and dry seasons as that ITCZ and the subsolar point migrate north and south. And so really just kind of highlighting the seasonality nature of it. We watched some videos, and this is really what drives the monsoon. And really you can see it from space, wherever the ITCZ is, which is where the subsolar point is, it has the most intense heating. It means air parcels are rising and clouds are forming. And so here you can see this cloud band. And over time, if you watch this video, you can literally track it. The cloud band moves north and it's wet and raining wherever that is, and then it moves back down south. And so there, when that moves further south, some of these regions then go from really wet to really dry. So now let's examine some of these similar the processes and the reasons why these circulatory systems occur, but now we're going to kind of bring it to a local scale and think about both here, sea breezes and land breezes. And so a sea breeze is a breeze that blows up from the sea, and so you have a high pressure over the sea, or for us, even on a smaller or more local scale, Lake Superior and inland. But then the land here, when a sea breeze occurring, you have a low pressure system or center over the land, and then you have intense heating, air is rising, and so air has to come in to make up then the fact that air is rising. And so you have a sea breeze blowing from the sea to the land, where you have a high pressure over the sea and a low pressure over the land. And then the reverse happens with a land breeze. So at night, and so this is often on a diurnal cycle during the day, the land is heating up. You go inland to like Ishpeming, and it's literally like 10 or 15 degrees Fahrenheit warmer than Marquette. You have this intense heating of the land. You have a low pressure center or low pressure system, at least locally, and the water is coming from the sea. But then going back to section 1 of land water differences, the land's going to cool down really rapidly overnight, and slowly that water was storing that radiation all day. And actually the water becomes warmer at night. So you have a low pressure system locally over the water. And so now air is rising over the water and drawing air from the land to the sea, known as the land breeze. And honestly, if you sit on the shore of Lake Superior, maybe even here in McCarty's Cove on a beautiful summer day, you'll get to experience both of these fluctuating during the day and then as it cools down toward night. The same properties then driving it in different locations around the world. And so a valley breeze happens for the same reason, but now we're going to think about it, especially in a mountainous valley. The ridge tops in a mountainous terrain get heated vigorously, have low pressure systems above the ridge top. They're drawing air up, and so air from the valley bottom is moving upslope to make up the fact that air is rising. And then the reverse happens at night. Your ridge tops cool down much more rapidly. Often the valley bottom is much cooler, moister, has more moisture, rivers, even lakes and wetlands. And so then you have the stored energy. And so air is going to descend from the mountain at night. And then in Arctic conditions, you have these really unique katabatic winds where you have extremely dense cold air flowing downslope under gravity, and they can flow at tremendous speeds. And so they're really like unique Arctic, especially across Antarctica, where there is dramatic topography. You can have these incredible cold, dense katabatic winds. Moving on to other mountainous regions. So here, especially in the Intermountain West region of the US, as we have air masses moving over from west to east, what can happen is you'll have a low pressure center on the leeward side and a high pressure center on the windward side. And so you already have this pressure gradient that's going to promote high to low. And so the air mass already wants to go from high to low. And so you're going to like create this enhanced condition where you're going to drive moisture up. It's going to cool. It's going to reach dew point. Clouds are going to form. It's going to rain, and then it's going to cool back down, or sorry, it's going to fall back down and warm up. My bad. And so to go backwards, it's cooling. As it's rising, it's raining, there's clouds, and then it gets to the top, it's descending, it's heating up, the pressure is increasing, and you have persistent warm, dry. And then what happens here, if you add this perfect recipe of a high pressure and a low pressure on either side of the system, you're just really creating a rapid conduit. And you have incredibly, especially the Chinook winds here being on the leeward side, very powerful, very dry breezes occurring. Moving into, for at least a slide here on ocean currents, you could take a whole class on oceanography and even a whole degree if you really liked oceanography. But here, oceanography in about one slide, we can think about these large gyres, which are circular movements of the ocean, of surface ocean water, and they're really driven by those winds that we talked about earlier. And so we have the subtropical high pressure generating descending and diverging winds. We have the trade winds, and so we can then couple that. And so as the ocean moves with those persistent wind patterns, they form these loops largely because the ocean water it runs into a continent and it has to go somewhere. And so even though it's being blown here from east to west, it then hits South America, gets deflected up towards North America, and then it gets deflected back towards Europe. And so it creates these really very well-defined circulatory loops in all of the world's oceans, or even in like sub portions of these oceans. Within the ocean then, for additional reasons, but here just for the scope of this course, appreciate that there's a lot of vertical mixing in the ocean, and there's locations where in the ocean they have these persistent downwelling currents. You have surface water funneling down into depths, and then you have other areas in the ocean that have these persistent or consistent upwelling currents, bringing this really nutrient-rich water up to the surface. And so wherever you have these upwelling currents, you have these incredibly, like this perfect recipe for incredible biodiversity. And so these really consistent upwelling regions around the world are world renowned for their marine biodiversity because of this continual like resupply of essential minerals and nutrients. So similarly, El Nino and La Nina here in one slide. And so what this really means is just simply a reversal of normal or average surface water temperatures along in the tropical region, so near the equator. And so when that temperature is above average, then we call that El Nino. And when the temperature is below average, it's called La Nina. What that really means is it really, especially here in North America, it can have this really profound effect on those air mass systems and where they come from, that influence North America. And so when we have El Nino, you often have this dominant of lots of air masses coming from the Pacific South, if you will, here, and then versus La Nina, we have more coming from the Northwest, and so further north, and then that's really like affecting weather on a continental scale. And so while this is like the measurable property of the ocean, it has influence on weather and ultimately climate the world over. So moving into climate now, what is the difference between weather and climate? Well, weather is the state of the atmosphere at a specific place on Earth's surface. So that's like now, what's happening in the atmosphere now or in the near term past or future. We can predict the weather, being a meteorologist, at least attempt to, versus climate is the long-term average values of weather, such as temperature and precipitation over time, what we expect. And so some major factors that influence climate include latitude. And so generally, like it's going to be colder near the poles and warmer near the tropics. That seems to make sense. However, seasonality is also affected. The mid latitudes, both north and south, typically have more seasonality or proximity to like to the ocean or not than really influences. So there's quite a bit of seasonality as well. So we're going to cover the 6 major types of climate, really 5 plus highland climates. And it was all then, or at least one of the most widely used, is called the Köppen climate classification system, which has been over the years updated. Often now it's called the Köppen-Geiger climate classification system. They're essentially, well, they are the same. They've just been slightly enhanced or tweaked over the years, but they nevertheless stem here from this major relationship between vegetation and climate characteristics. And those climate characteristics are based upon temperature and precipitation. And so we can think both like annual totals, as then if we plot it and look at it over a month, we can also examine seasonality. So both totals as well as average, and then including seasonality. And we can then, as described within the climate lecture, there are these major climate regions, denoted by capital letters, and we'll go through the major ones. And for this course and for a quiz or an exam, I'm really just going to encourage you to be able to compare among major climate regions, and just appreciate that there's subdivisions based upon moisture and temperature conditions within each of these major climates. However, for the exam, I'm not going to quiz you on any of these subdivisions, but here, tropical and arid climates, number A, surround the equator, and really they kind of exist north or south by 25 degrees latitude, and they're consistently warm temperatures or even hot. The tropics really being dominated by the subtropical high pressure system at 30 degrees north and 30 degrees south are hot, but they're also dry, so low amounts of precipitation. So as you may expect with the term arid and semi-arid, now you have hot, dry conditions, where tropical are hot and moist, or at least humid conditions. So that was A, and then B, and now C. They are known as temperate, also known as mesothermal. They're interchangeable terms. So these temperate mesothermal climates, as C, are southern mid-latitude, if you will, and they have distinct warm and cold seasons, where, especially in the tropical climates, there's very little seasonality. It's pretty much just hot and humid all year round, versus here in these more southern temperate regions like Florida and Alabama, for example, you're thinking like they have distinct warm and cold seasons, but it's warmer than colder in general, whereas as you move further north into the D, this is known as continental, also known as microthermal. And so now from 35 north, moving a little further north to 60, we have longer cold seasons being a major difference between temperate and then limited warm seasons. Moving even further north, so north of 70 or south of 70 degrees latitude, in non-mountainous regions, we call those polar climates as E. And so you have these long, cold winters, and they're actually kind of like literally cold deserts in their own way because there's very little precipitation in these Arctic regions. It just doesn't really melt or hardly melts. And so the little bit they receive tends to stick around a while. So highland climates being their own unique, and a big difference here is they can occur really at any latitude, and they supersede latitude. And just because of these major elevational differences with pressure and temperature, you have a unique zonation of climate. And as we'll learn into the biomes, you have this zonation of biomes that mirror that climate difference. We can reconstruct past climates, and we can do so at different time scales. We can use what's known as proxy data that provides clues about past conditions. And so these clues contain like examining tree rings or taking pollen records out of wetlands, for example, and carbon dating them, and then looking at the presence or absence of pollen, and that can indicate climactic conditions, and the growth ring size indicating climactic conditions. There's also what is ice core data, which we've covered extensively. And really, this is much more quantitative and analytical in nature, where literally scientists are retrieving deep ice cores from glaciers all over the world, analyzing them, comparing the results from ice cores from both hemispheres, northern and southern hemisphere, from northern Asia, Eurasia to North America and beyond. And so there's many locations where these ice cores are being removed. And then, as I described, they can analyze a suite of chemical properties, including concentrations of gases, isotopic concentrations, which then allow us to literally determine air temperature. You can date these materials like carbon dating. And so now we can reconstruct past climates by analyzing both the meltwater as well as the trapped air inside of those ice cores. And by combining them, we can look at carbon dioxide concentrations, we can look at methane concentrations, isotopic concentrations of hydrogen and oxygen that allow us to estimate and determine temperature. And we can put it all together, and we can reconstruct climates. And some ice cores actually go all the way back to 800,000 years. And so it is a very quantitative and empirical method of reconstructing past climates, understanding that there's this very much natural cycle of warmer periods, which happen to correspond with larger amounts of CO2, and colder periods, which happen with lower CO2. And it kind of goes under this approximately 100,000 year cycle of warm and cold and warm and cold. And as we'll talk about a little bit, and we did more extensively in the past, we're able to overlap these ice core data with real observations from places like Mauna Loa Observatory. So this is actual atmospheric observations, and then we can overlay them with recent ice core data to prove or corroborate, like validate this method, to show that the ice core is representative of these past conditions. And then moreover, now by reconstructing, we can compare, and we do understand that our current atmospheric conditions have more carbon dioxide in the atmosphere than at any point in the last 800,000 years. And while some episodic events like asteroid impacts or volcanic activity may have fairly temporarily caused really big differences that may or may not get picked up at some of these time scales, those events can have dramatic climate change. We'll talk about that next. But here, we as humans are very much altering the composition of our atmosphere. This much is known, where our current concentrations of CO2 exceed 400 parts per million, and that this is different. We know carbon dioxide is a greenhouse gas, and that therefore things are different. Things are going to warm up more because we have more CO2. what's going to happen next, we're not exactly sure. And so refer to past lecture content and some of the activities to dive into that topic in a little greater detail. But here, returning then, just appreciating like super volcanoes like Yellowstone, among others, as well as asteroid impacts like the Chicxulub crater that wiped out the dinosaurs, or the Sudbury impact that happened here, or at least not too far from here in Marquette. It happened in Sudbury, Ontario. These type of events are catastrophic, and not only are they instantaneously at that time catastrophic, they have like decades, hundred thousands, and even like tens of thousands of years of impact. At least these mega events like the Chicxulub crater and the Sudbury impact and mega volcanoes can literally change climates like dramatically. And so these have very, very powerful implications if and when they do happen again. There is another reason why there's natural climate variability. And really, to go back to this, it describes, it really proves through a lot of like physics and chemistry, but through physics, we can understand the radiation balances of Earth. And so this cycle of warm, cold, warm, cold, warm, cold that happens at approximately 100,000 year cycle or so happens to line up literally as we estimate and quantify how much radiation is received by Earth due to these three differences, which I'll cover next. It happens to like perfectly line up with those warm and cold periods. And so what are they? So this is a natural cycle, which is called the Milankovitch cycle. It includes three major parts. Part one is orbital eccentricity, showing that at about 100,000 year cycle, the Earth goes from a nearly perfect circular orbit to a very expanded elliptical orbit and back. And that change, then you can estimate, literally quantify what the difference of radiation received by Earth's surface due to this difference in orbit. Our tilt, as we know, is at 23.5 degrees, and for our lifetimes, that is fixed. But however, at approximately 41,000 years, our tilt actually varies from 21.5 to 24.5 and then back. And so we did focus a lot in section one on the role of this tilt and how much it drives radiation balances on Earth. So you can appreciate that changes in the tilt also then change our global radiation balance. Finally, part three, last but not least, so if you spin a top, for example, or at least if you were looking straight down on that tilted pole, so now you're looking straight down on it, the tilt might look like this at this moment, but actually over this more like 10,000 year cycle, our tilt, our axis is moving in this orbital precession, the wobble, and then literally that is also very much affecting these radiation balances. So these are three known natural processes that influence radiation, and they overlap and very much closely correspond to these dramatic warming and cooling cycles as we understand radiation budgets on Earth's surface. A little bit about carbon and the carbon cycle. I mean, mostly appreciate there's lots of carbon on Earth in many forms, including as carbon dioxide or as these inorganic carbon in deep fossil or deep sediments. So these are all reservoirs. There's carbon in the atmosphere, there's carbon in the oceans, there's carbon in trees, there's carbon in us. And so each of these reservoirs or pools stores carbon, and we can subdivide them really into active pools of carbon. Anything living is a very short geologic time span in our atmosphere in general. But then here, inactive zones, so like deep ocean sediments and then far beneath the Earth, these locations where carbon is stored really like don't change much or shouldn't change much. And I should say, in terms of like they take a really long time to return to some active zone. But however, we have as humans have been rapidly extracting these inactive carbon resources, reservoirs, and then mostly combusting them, being emitted as carbon dioxide. And so this has disrupted this natural global carbon cycle, and largely it's all coming from fossil fuels, which I think are really cool in that all of our fossil fuels used to be living organisms that died, and now we're literally extracting them from the earth, and then the intentional, or rather the not so positive consequences of this then is the fact that we are altering the climate. But geologically speaking, I just always kind of am amazed. Like, think about the Everglades of Florida, it gets buried, and then over time it compresses, it turns into a form of fossil fuel. It could be natural gas, oil, or coal, or all three of them. And then that, like, literally what we're doing is we're extracting like paleo swamps from around the world, just like the Everglades. Okay, so let's wrap up this review and focus on biomes for a little bit, as well as ecosystems. So ecosystems are communities of organisms that interact in interdependent ways, basically a group, a community of organisms. And so now we can connect climate and biomes through biogeography, which is really this geographical distribution. There are certain habitats that exist around the world, and they exist in those regions for many reasons, or for a few reasons, often driven or likely driven by climate. And so here we're going to link climate and apply what we learned about climate within the scope of biogeography. So components of ecosystems include the living and non-living parts. And so the living parts known as biotic and the non-living parts known as abiotic. Within the biotic part, there are many different types of organisms, including ourselves, things larger than us and smaller than us, and things incredibly small. And so here to appreciate some major categories of biotic organisms. We have autotrophic organisms that produce food from light or chemical energy. We have heterotrophic organisms that require consumption of plants and other animals for survival, like ourselves. And then we have this special class, one of my favorites, called decomposers, that exclusively feed on dead plant and animal matter. There are many types of decomposers. However, the world over, there's an incredible amount of microbes, both bacteria and fungi, that are these incredible decomposers. And we'll look at soils in the future and talk a little bit more about that. So a little bit about the food chain, really kind of coming from primary producers, being plants or autotrophs. Then you have plant consumers, so herbivores eating the plants, and then you have levels of consumers like other heterotrophs that eat eat herbivores that are eating the autotrophs, and you can go up many levels depending on your ecosystem, but they often come full circle through this unique class called decomposers. Within any ecosystem around the world or a biome, you can really track all elements from water, oxygen, and hydrogen to carbon to nitrogen, and think about how these different organisms are interacting and or affecting all these different cycles. Biomass is an indicator of plant productivity. It is, as definition, the dry weight of all living organisms. So latitudinally around the globe, there's regions like tropical rainforests that have an incredible amount of biomass because you have these like great growing conditions. It's warm and sunny. And so other regions where it's hot and dry have very less. And so it's a good kind of general indicator of plant productivity around the world. And then it reflects the amount of stored chemical energy available for consumption. So now we're going to kind of like classification of climates. We'll focus on biomes here. And so climate being the most important factor influencing the geographic distribution of vegetation. So biomes are definable geographic regions that are mapped according to predominant organisms and vegetation. And so what does that mean? Basically, you have these definable groups of organisms, and we're going to subdivide them into major biome types here, kind of like climates. While in the lecture, we explored in much greater detail subdivisions within these major biomes. Here for the exam, I'd like you to just be able to compare among major biome types of the world. And so a forest is a region dominated by trees. It needs to have a net surplus of moisture, or at least lower typical atmospheric temperatures, so average temperatures, but largely dominated by this net surplus because you need quite a bit of moisture to support something as large as a tree in terms of vegetative growth. Whereas then forest to grassland, we have continental and temperate locations. You have these grasslands that are in tall, humid areas. And so you have this tall, like denser and more humid, and then often sparser vegetation and slightly semi-arid conditions. But either way, an area dominated by grass, and it still needs enough humidity and moisture to support that much plant growth. Whereas somewhere like a hot and dry desert has very little vegetation, and they have these unique adaptations the vegetation does to conserve water for incredibly long periods of time because there's hardly any of it. And so hot and dry deserts, perpetually hot temperatures, and they have unique vegetation known as xerophytes. Within deserts, we can kind of look at semi-arid, so it gets a little bit more moisture, and look at cold desert biomes. And so here you might have cooler temperatures, but you have a very little amount or low amount of moisture, so there's not much to go around. And so in these more semi-arid and cold desert locations, you will have some vegetation, but it's pretty sparse with large patches of bare ground. So moving in here from pretty extremes of like hot and dry and cold deserts to Arctic tundra. And so here, Arctic tundra located in high latitude, colder and drier parts of the subarctic region. So both in northern D climates, then like continental, microthermal, as well as polar regions. And our highland climates then superseding, you can have high elevation tundra biomes. They actually have very similar or literally nearly identical vegetation conditions, both at high latitudes as well as high elevations. And these vegetation communities dominated by mosses, lichens, some algae, sedges, and stunted shrubs. Some local aspects that influence vegetation communities, including slope. So the steepness of a slope is going to affect vegetation communities. A really steep slope is not going to be able to retain much water. So when it rains, that rain usually is going to run off. And so therefore it's not storing that water. And so as a result, you're affecting vegetation communities just purely based upon how steep a slope is. So flatter areas retain more water, steeper slopes typically do not retain nearly as much water. The aspect is also incredibly important, and so that is the compass aspect that the slope is facing. So especially in the Intermountain West region, you can have these really dramatic differences. So a south-facing slope often is really dry with sparse grassland, stunted shrub vegetation because there's so much heating and so much evaporation that even though both slopes receive the same amount of precipitation, this one is literally has tremendous amounts of evaporation. It's losing that moisture, and therefore there's less available to plants, whereas a north-facing slope can be much more densely vegetated and even go from a forest to a dry grassland, so a steppe or semi-arid grassland, just based upon slope aspect. So here in the Upper Great Lakes region, we have similar influence. However, it's typically not as dramatic, where we might have different forest canopies dominated by more moist, cool, loving tree species on north-facing slopes versus some of our tree species like jack pine and red pine that are more dry adapted, dominating our south-facing slopes. So a little bit about vertical zonation due to these highland climates. And so our vegetation in all across the Intermountain West and any mountainous region around the world changes because cold air holds less moisture than warm air. And then as air parcels are rising, they're cooling, and they're also getting colder and colder and colder. And so you have this change of precipitation as the air parcels move up, and then at some point they get so cold that really nothing can grow. And as a result, it often produces this very, like literally very definable sequence of vegetation conditions going from deciduous to coniferous to alpine, kind of taiga is what they refer it to, kind of an ecotone between coniferous and tundra. And then finally tundra, you're above tree line, and then just bare rock and ice at some point with like even tundra vegetation can't survive. And so really we see a really similar transition as you move north away from the equator or south towards the poles. You kind of are going across like degrees of latitude, but you're doing it in a very short space within mountainous regions. So after a major event like a fire or a landslide or a volcanic eruption, you're kind of like hitting the reset button on that community. And so this sequence of succession happens where you have this primary succession. So only pioneer species will um, vegetate these like newly disturbed slopes. And so that's known as primary succession, being dominated by this kind of small subset of plant species known as pioneer species that are capable of tolerating really harsh conditions. It's really hot, it's really windy, there's not a lot of available moisture. And so some of our more like intermediate succession or climax community species simply can't tolerate those harsh conditions. But once it stabilizes and some of these primary primary succession species as pioneer species, once they establish, they regulate the environment a little bit and they allow for other types of trees and other species to then establish themselves. And once established, our secondary species can then like literally become, it regulates the environment even more. The soil is stabilized. It's not as dramatically hot and cold. It's a little less windy. And so it's providing this kind of more structured habitat. And eventually over time, you have this known sequence from primary to secondary, and ultimately for any given region. And for us here in the Upper Great Lakes, we have this kind of dominant mixed deciduous forest dominated by maple species as well as white pine. So you have this kind of known sequence here of plant succession. Finally, last but not least, and a little throwback to my days in the desert, riparian zones are pretty cool. And I got to, in fact, study them and spend a lot of time in desert riparian areas. But generally speaking, a riparian area is a zone immediately adjacent to the stream. And because of that, the plants that are immediately adjacent to a stream have this abundance or access to abundant amounts of precipitation compared to like further away from the stream. And so they have their own unique corridors of ecosystems known as riparian zones. And so with that, Dr. VG is signing off.